Remember we were talking about virtualizing the processor? This whole concept of virtualization is very, very important, but we started talking about virtualizing the processor, giving every program this notion that it is the only thing running on the computer hardware. And we also mentioned that it would be really keen to be able to virtualize memory, but we aren't talking about that yet. So you kind of are going to have to suspend your disbelief a little bit as we go through this, because we're going to make decisions that are slow and inefficient, and that's just the way it's going to be until we actually get around to virtualizing memory. So I just want to make sure that I say that up front so that you don't think that we're creating some idiotic abstraction or idiotic design. There are definitely issues that we will address. You kind of have to do all of them before everything gels and makes total sense. So anyway, the notion of a program as it's running, so you need all of the context, its register state, its memory state, stack pointer, all of that kind of stuff. All that together is called a process. So it's the program as it's executing and the context of the program as well. We need to have all of that information. And yeah, I already described this. And so we're going to presume we have a way of capturing this. It turns out to be extremely straightforward to capture all of this information. You'll see examples of this on assignments 6 and 7 that actually very closely mirror what operating systems really do. There are other things, though, that we haven't gotten to yet, which is the question of who actually manages all the processes, because we said that processes have a constraint that they can't mess with each other. They can't observe each other's state. They get exclusive access to the hardware. Something has to be able to see everything if we're going to be able to do this. Also, we'd like to be able to actually interrupt a program. We had the whole thing that we could do cooperative multitasking where a program decides, all right, I'm done with the CPU, I'm going to be nice and give somebody else the processor. But that's not very good, because if a program decides to go haywire, either intentionally or accidentally, then we have the whole system gets locked up by that one program. And so it'd be really nice to have somehow a way of interrupting the program so that something else can start running. So that's the whole notion of how do we interrupt a program so that we can context switch away. Also, programs are sometimes badly behaved. We have all written badly behaved programs, probably a lot this term. And I write badly behaved programs all the time, and then I have to fix them. So we'd like our computer abstraction that we're sort of developing here, we'd like it so that when one program crashes, it doesn't unhinge everything. And so we'd like to have a way of figuring out, okay, this program died, so maybe we can handle the situation gracefully and then maybe switch to another program that's running. So first question, process manager. What if we actually had a second processor that we built on this physical device that we're building? So we have one for the program and we have one for the controller. And like I say here, the controller processor is able to access everything, and the program processor is only allowed to see the stuff inside the box. And so somehow magically we get the controller processor to step in, and it can do context switches. It's able to interrupt the running program and copy the stuff inside the box out somewhere else and so forth. We could solve the problem this way. Does this seem like a good idea? Yes? No? Why would this be a bad idea? Do operating systems ever have bugs in them? It's been known to happen. Yeah, I'm seeing no. I hope you're being sarcastic. Yeah, so that's the challenge. Is that, well, if we build this stuff in hardware and then we have to change it, then we're stuck. Okay, there's another interesting assumption, though, about this. How often should the control processor be doing things? Like, should it be doing stuff all the time? There's kind of a reality of these systems that the more time we spend managing stuff, the less time we spend actually doing useful stuff. It's kind of like an allegory to the real world, that the more time you have managing, the less time you have doing. And so you'd like to be managing as little as possible. You'd like to actually be spending most of your cycles doing real work. And so these are a number of the reasons why we don't like this. Okay, if we have a separate control processor, we're already starting off on the wrong foot, because we're presuming that I'm going to be spending a lot of time managing as opposed to actually doing. Okay, so it doesn't really justify a separate processor. Also, when we mess things up or we want to add new facilities or things like that, then it really curtails our ability to do that. I'm sorry, could you guys stop whispering? It's really distracting. So what we can do instead is virtualize the control processor. Okay, so now we're going to say, hey, let's have a special program, and it is going to also sometimes get the physical processor. And of course, now we have an interesting thing where we'd like the control process to be able to access all of the hardware capabilities, but we don't want everything else to have those capabilities as well. So we need to have some way of making this control process special. Okay? The way that we do this is that processors now have multiple modes of operation, where we can actually have the processor itself in hardware physically enforce this distinction between application processes and control processes. And so we have a couple of different modes. We have kernel mode, where basically the program could do whatever the hardware supports, so I can actually control all of the little settings that allow the system to do what it does. Okay, so I have special instructions and everything like that. We call this also protected mode or privileged mode. And then we have the mode for applications. We have user mode. We can actually constrain what programs are allowed to do. They can only see their own things. They're not allowed to execute special instructions that control things. Okay, so you don't actually allow the applications to change the configuration of the hardware. Okay, so that's user mode or normal mode. And so the control process now starts to become a trusted intermediary between the rest of the programs and the computer hardware itself. And so like I say here, it is supposed to be trusted. And usually people do a pretty good job when they create these control processes. So if you ask yourself, well, what does it mean to say that this is a kernel? It's just a part of the system that runs in kernel mode. That's really all it is. Okay, so yeah, like I say here, the program becomes the core or the kernel of an operating system for our computer. And it's an interesting detail that we don't have everything running in kernel mode, because that would kind of be a dumb way to do things. A lot of operating systems have all kinds of facilities that aren't actually required to run in kernel mode, like being able to list the files in a directory. There's no reason to have that be in kernel mode. Having a heap abstraction, there's no reason to have that in kernel mode. So the operating system sort of has as much as is in the kernel as is necessary or expedient, and then the rest of it is outside of the kernel. Okay, so there's several purposes. Manage computer hardware on behalf of programs. Okay? The operating system is kind of like a government. It sets up an environment in which applications can do their things, but really the best kind of governing is the governing that helps you do your job but doesn't get in the way. And so that's what the operating system is really responsible for. Okay, an abstraction of the processor to support concurrently executing processes, including isolation and making sure to handle program crashes gracefully, and in other common facilities as well. File systems, memory management, so that we get into virtual memory management, which we'll talk about probably starting next week, networking operations, and so forth. So when we want to have a clean way of doing this, because I may have a solid state drive, which has one way of interacting with it. I may have a spinning magnetic disk, which has another way. I may have flash drives. I may have CD-ROM drives, and so forth, or optical drives. And the operating system also provides a unified API for working with all those things, so that programs don't have to talk to hardware directly. Now the programs get to talk to the OS, and the OS talks to hardware for it. So this extends our abstraction hierarchy. We already talked about computer hardware. The OS now sits on top of the computer hardware, and it mediates the hardware usage between or among applications that are using it. We have simple APIs or application programming interfaces so that programs can use them, and the OS sort of simplifies the life of program writers. And then we have the application sitting on top of that, which solves specific problems, like I say here. So you have a compiler, database server, I have a web browser, so forth. And then you have people, okay? Or what I should really be more specific is users. And this is a really good way of thinking about it, or clients of the application, because sometimes your application is a server that other programs talk to. And so you can build up networks of distributed systems that are able to interact with each other and work to accomplish things. Okay, so this is our series of abstractions. As you can see how each one sort of obscures the thing below it, because we'd like to be able to present a simplified abstraction on top of each thing. Okay? Now, IA32 is interesting because it actually has 4 different operating modes. I don't mention it here, but the ARM processor, like a lot of cell phones use ARM processors, they have 7 operating modes. They have 7 different operating modes. Because if you think about it, the software that allows you to play Angry Birds or whatever your favorite game is on your phone should be allowed to do certain things, but not if you're in the middle of a phone call. So being in a phone call is in a different operating mode, and being in hibernate or suspended mode is in another operating mode. And so you have these modes that allow the phone to constrain what the applications are allowed to do in various states. So that's why we have so many operating modes on mobile processors. But IA32 has 4, and the reason why is because not every software component that runs on the hardware should be allowed to do all the things that the hardware allows us to do. Okay? So if we package things up and put them into different operating modes, then we can actually sort of buy ourselves a lot of security or stability in our operating system implementation. Okay, so I don't know if any of you have had this experience, but back in the days of Windows 3.1 and Windows 4, and then starting even in Windows 95, you'd have the errant printer driver that would bring down the entire operating system. It's like, okay, really? This is a printer driver, and it's bringing down the whole system. So we have situations like that we'd like to prevent. So if you put that device driver into a separate mode, then it can't really mess up the core operating system. Okay, so we partition the OS code into privilege levels, and these modes form a hierarchy. Level 0 all the way to level 3. Level 3 is where the application runs, typically, and level 0 is where the kernel lives. And you can see that they form sort of a ring. So you can do in level 0 everything that you can also do in level 1. Level 1 can do everything that's also in level 2, and so forth. So ring 0 can do everything. I like to call them rings as opposed to levels, but in the lecture I wrote it as levels. Okay, so the kernel runs in level 0, services can run at 1 and 2, and applications can run at 3. So the next thing to talk about, and we're going to spend a little bit more talking about operating systems and privilege levels, because it doesn't work exactly the way I sketched out there. But like I say, how do we actually trigger the context switch? We need a way of getting the hardware to interrupt the current program, because we say that we have an abstraction that the program has sole access to the processor, but while it's running, it does. It really is the only thing accessing the processor. Okay, also, if the program misbehaves, we need a way of transferring control. So you might look at this and start saying, hey, this is starting to look a lot like exceptions again. Okay, remember we talked about in Java or C++ being able to throw an exception. Well, we'd like to be able to do the same thing at the hardware level. And so programs have a logical flow. Remember that each program, it looks like it's flowing, execution is flowing through the program. In reality, we're hopping back and forth between programs, but we have a third kind of control flow where we can actually interrupt the logical control flow of a program. Okay, so the loops, conditionals, and so forth, those are all parts of the logical control flow. So we'd like to be able to handle exceptions as well. And this is things like timer interrupts that might allow us to switch to a different program execution. When the program accesses memory in an invalid way, we'd like to be able to handle that as well. So we call that exceptional control flow. There are 2 major sort of categories as to what can cause exceptional control flow at this level. We have interrupts, which are hardware-based. So I have a timer, a hardware timer on the processor. I set it up, and it goes off, and that generates a hardware interrupt. Or the disk controller says, hey, your data finally showed up 8 million clocks later or whatever, so you get a hardware interrupt that you can go ahead and do that. And like I say, it's usually not caused by the execution of a specific instruction. Exceptions are software generated. Okay, so like I say, it can be caused by a program executing an instruction, and it can either be intentional or it can be accidental. Okay, either one of these situations can occur. So you have interrupts and exceptions, and usually this is how the terms are used. Now the other thing about hardware exceptional control flow is that it really isn't like the way that programming languages work. Because we're used to in C++ or in Java or in Python or whatever language you're using that has exceptions, that when you have an exception occur, you just stop doing whatever you were doing and you leave. You're done. You get out. And that's not the way that hardware exceptional control flow always works. Because there's a lot of situations where an error occurs and you say, I think I might actually be able to solve that problem. And so you go to the exception handler, you try to do stuff, and then you go back and try again. And so you can see that hardware exception handling is a little bit different than the way we think of exception handling in program languages. Sometimes we like to retry, or we like to resume at the next operation. So these are sort of the 4 kinds of exceptions that can occur. So you have interrupts, again, which we talked about a little bit already. So we have a hardware signal that occurs, and so that's an interrupt. We have traps, which are intentional exceptions. So the software generates a trap. And you'll notice here that both interrupts and traps go to the next instruction. Faults are errors that we may be able to recover from. So we go back to the instruction that caused the fault and try it again, which could lead to really weird kinds of infinite loops between your operating system and your application. If you think you handled a fault and didn't, and it faults again and again and again. And then you also have aborts, and aborts never come back. So aborts are kind of like our software exception handling, where we never go back to the code. In fact, we don't really go back to anything. We just kind of suspend the hardware because we think this is something that prevents us from doing any more computations effectively. And so these are sort of the 4 kinds of exceptions that you have. The other thing that I wanted to mention, we talk about returning to the next instruction. It is not possible for an interrupt to be dispatched in the middle of an instruction executing. What happens is even if the hardware says, hey, there's a hardware interrupt, we're in the middle of a divide instruction, which takes many clocks to perform, then what happens is the processor sort of says, okay, I will deal with that, and so when the divide finally finishes, then that space in between the previous and the next instruction, that's where the exception is handled. So that's why we say we return to the next instruction, because we never really interrupt an instruction. Obviously, a fault kind of is the instruction itself fails, but then after you've determined that it fails, then you go handle the fault, and then you come back and retry the instruction itself. Okay, any questions about that? Does it make sense? Yes? Well, so that basically is the responsibility of the handler to make sure that it doesn't modify state in a way that prevents the previous instruction's state changes to be visible by the next instruction. We'll actually talk about that in a moment. But yeah, so you can imagine the handler is responsible for saving all register state. It's responsible for saving stack state, flag state, because it may be that you interrupted a comparison. Those kinds of things. So all of that state has to be restored by the handler before it returns back to the next instruction. Yeah. Any other questions? All right, yeah, we will talk about that, but we probably won't talk about it as much now that we've talked about that here. Okay, so interrupts caused by hardware, so I already talked about this. Traps, boy, I just went through and already talked about a lot of this. Traps are interesting. Traps are basically the way that applications can call into the operating system. So what we do is we set up the registers in some way to say, this is the thing I want you to do because I can't do it. I want you to set a timer interrupt for me to go off at a certain time so that I can wake up. And the operating system has to do that because it involves hardware. And so the caller sets up the registers, traps into the kernel carries out the responsibility, and then returns back to the application. So this is sort of how we provide operating system calls. We'll talk about this a lot more next time, I believe, when we get into trap handlers. Okay, faults, unintentional exceptions caused by the software. So the example that we will be studying a lot in a few lectures is how hardware virtual memory support works, where a program thinks that an address is correct, and so it goes ahead and tries to access it, and it generates this thing called a page fault, because the data is actually not in memory. We'll talk about why it's not in memory, what in the world this all means. But let's say that the data is not in memory, but it's stored to the disk. And so the program, when it accesses that thing, generates a page fault. The operating system gets the fault. Okay, so the operating system handler gets called, it receives the fault, and it says, okay, yeah, that's a page that I actually have on disk right now. I don't have that in memory. And so what it does is it pulls that data, stuffs it back into memory, and then when it returns from the fault handler, it goes back to the instruction that actually caused the fault so that we can retry. So that is a simple way that we're able to provide a virtual memory abstraction. That gives you a clue as to what we're going to be doing next. And of course, the operating system fault handler may say, actually, you know what? You tried to access null. You tried to dereference null. And that also generates a page fault. And so the kernel says, you know what? There is no valid page for that address. So instead of trying to load it from disk, what I'm going to do is actually just terminate the program and inform whoever that needs to know that the program is stopped and it's not coming back. Okay. So these are the kinds of things we can do with faults. And then aborts, unrecoverable fatal errors. There's basically, on IA32, there's only a couple of aborts. And the one that is the worst is machine check, because it basically means all hell is broken loose and we don't even trust the computations to be correct anymore. And so the OS typically just says, hey, I give up, fix me, and that's basically it. So you get kernel panics can be in that category, and the Windows blue screen of death can also be in that category. Although, really, when you're getting to that point, it's even worse than a BSOD or a kernel panic, actually. It's even a little bit worse than that. Okay, let's see. Any questions about any of these? These are all going to become very important concepts as we go forward, so hopefully it'll all be very clear to you. Now, I'm getting into how IA32 does this. We're going to necessarily get a little bit involved, and I hate to because it's just grungy, but we have to. So IA32 has 256 different kinds of errors that can occur. And they're all assigned numbers, 0 to 255, and 0 to 31 are hardware-generated interrupts and exceptions, which is really nice. So these are sort of a fixed standard set of exceptions. There's a few here that I'm going to show you. I think it's kind of cute that exception 0 is divide by 0. It's like interrupt 0 occurred. You divide it by 0. So, for example, if you try to do a div and the denominator is 0, then you actually generate an exception. You generate an interrupt. The ALU generates it. Okay. Exception 13, general protection fault. So if you try to access a piece of memory, you try to write something that's read-only, it'll generate exception 13, and the operating system will get it, and it'll generate a fault that your program gets, and it will probably kill your program. Okay. And then there's a few other ones. There's bus errors. Bus errors tend to be when you try to access memory in a way that's not supported. Like the PowerPC Max would generate bus errors. And the reason why is because you were trying to access memory in a non-aligned way that wasn't supported by the hardware. And so it would generate a bus error. Exception 18, machine check abort. So that's another one. Okay, so there's a few things like this. Okay, so you have those 0 to 31, and those are pre-specified as to what they're for. 32 through 255 can be used for pretty much anything that the operating system wants. And there's a whole bunch of ways that the OS can manage this stuff. There's this thing called a APIC, Advanced Programmable Interrupt Controller, that's on the hardware itself. And the OS, as part of the bootstrap process, will go in and configure that APIC to say, I want these devices to be associated with these interrupts. I want these interrupts to be used for this and that. So basically it can go in and configure all that stuff so that the hardware devices can communicate with the OS properly. Now, usually there's a specific trap or a specific interrupt that's assigned to operating system calls. So on Unix, it's hex 80. There's a few other ones, like I think Windows uses interrupts 25 hex and 2E hex. I can't remember all the details, but there's various ones that operating systems choose to use for applications to communicate with the operating system. And the way that applications can do that is there's a special instruction called int, which allows you to execute that interrupt. Okay? So you say int n, you say int 0x80, and that'll call into the Unix kernel. And the kernel will look at what you ask and decide to do it or not. Okay? Let's see. Now, what happens is, obviously, the hardware needs some way of allowing the OS to specify what handlers to invoke when a particular interrupt occurs. And so all of this is done through a giant table. It's not that big. It's called the interrupt descriptor table, which basically says for each interrupt what to do. Okay, and so like I say here, the exception type is used to do that. This is a little bit different than what you may be familiar with from 5X, and I want to sort of point that out right away. The interrupt descriptor table has 8-byte entries, and the entry says what protection levels, like what protection level is allowed to generate the interrupt, what protection level you switch to when you go to the interrupt handler, and also what's the address of the handler. So those are the things that you can do in the interrupt descriptor table. And so, yeah, exception n, it just takes n, multiplies it by 8, and then adds in whatever the interrupt descriptor table register holds. So the interrupt descriptor table register is the starting address of this table, and it just takes that entry and uses it to dispatch the interrupt. Okay, so this is how interrupt dispatching actually occurs at the hardware level. Okay. I want to just mention this because there's also the interrupt vector table, and that's what people in 5X typically use. That's 4-byte entries. That's just an address to jump to. I'm pretty sure there's a way to get IA32 to do that, but I don't remember off the top of my head. So, but anyway, this is what we do in protected mode execution. We do the interrupt descriptor table. Okay, so yeah, these things are called gate descriptors, and they have basically exactly like what I was describing because we have these different protection levels that we have to think about. The application's in protection level 3, and the kernel's in protection level 0, and somehow we have to allow that transition to occur. And even if you have a hardware interrupt, you have the timer goes off while the application is running. Well, we're in ring 3, and we need to transition into the kernel in ring 0. So even the timer interrupt handler has to be able to say, hey, send me to ring 0. Okay, so we have several different kinds of gates that we can use. I don't want to go into too much detail because I don't want to get lost in the weeds, but we really care about interrupt gates and trap gates. Those are the ones that allow us to transition into the operating system kernel. But there's also call gates, which allow us to transition into different protection levels using call or jump instructions, and task gates, which use a special task facility that's built into the hardware that allows you to do multitasking. Most operating systems don't actually use the task support at all, which I don't know. It seemed like a good idea at the time when Intel designed it, but nobody uses it. And so they have to keep supporting it, but nobody uses it. And these gates are very simple. Remember, they have a start protection level, an end protection level, and the address that you want to transition to. So if the caller has at least privilege level A, jump to the handler at privilege level B. That's basically all the gate does. Okay? And so a good question is, why are these things called gates? And remember, when we have these privilege rings, where I'm in level 3 and I'd like to be able to do something in ring 0, I can't just go ahead and call that code. The hardware actually has support for saying this memory region is only accessible by ring 0. So I can't just jump to it. And even if I could just jump to it, if it tried to do privileged operations and I'm still running in level 3, it's going to fail. And so I can't just jump to code and have it magically do stuff. So we have to enter through gates. You can think of it just like a castle. I've got the moat around the outside, and there's that one drawbridge that allows me across the moat. And then I get inside the castle itself, and there's the region around the castle. And then there's a castle, and I have to get into the castle, and then there may be various areas in the castle. So it's the same idea here. You have gates that you have to pass through. Those are sort of the inspection points, where I'm allowed to go into this region or I'm not allowed to, and I'm prevented access. So these are sort of the way that the hardware is set up. Okay? Now you can see in this picture, I have, 7 different gates. Real operating systems don't have nearly this many gates. We tend to have just a very small number of gates where all the operations go through that very small number of gates, and then we go ahead and handle things just in those few places. Because it's these transition points that are particularly susceptible to errors. And if I just have a small amount of code, they have this saying, it's like more code means more bugs. And so there's another reason why we like to have our programs be as small as possible, because There is an average bug rate that people tend to write code with, and so the less code you have, more likely you'll have fewer bugs, and you track them down and fix them, and then your entire system is more reliable. So this kind of approach isn't particularly ideal. And so most OSs generally have just a few gates, and then they just really inspect the code that handles those transitions to make sure it's accurate. Okay, so we can manage privilege levels. We can do things like this. If the interrupt or fault or abort handler has to do privileged operations, which almost always it does, then we just jump to the higher privilege level before executing the handler. Okay? The program was interrupted. It can't affect the handler anyway, so we're okay. Now, trap handlers are a little bit different because this is the application communicating to the handler. And so we start out at the low privilege level, we do some inspection, and then we transition to the handler. Or maybe, as is the way that OSs typically work, is we jump into the handler, we inspect the data that was passed from the lower privilege level, and if we trust it, then we go ahead and carry out the operation. So in the trap handler, you have to be extremely cautious. In interrupt, fault, and abort handlers, you don't have to be as cautious because it's hardware transitioning, not the application. It tends to be a lot more difficult for applications to screw up fault handlers, for example. Okay, so lowest privilege level on IA32 is 3, highest is 0, which is weird, but that's just the way they decided to do it. And we could partition our operating system code thusly. We could say, well, level 0 will be the most critical stuff, level 3 is applications, level 2 might be entry points, and level 1 might be things like drivers, so that they can't screw things up. Okay, so we could do something like that, where the application transitions, the handler looks at whether or not it's allowed to do stuff, and then maybe calls into the various other things that it's allowed to do. Okay, so we could do something like this. But weirdly, this isn't how operating systems actually work, because this does introduce a lot of complexity. And so in reality, this is the way that it's laid out. Level 3 is user applications. Level 0 is the OS kernel. That's the castle. And everything is in there. And then you have level 1, which is sometimes used for virtual machines. So for example, like I say, you're talking about the same example we had before, is that I want to change a password. Well, level 3 goes straight into level 0. The kernel looks at the request, decides if it's acceptable, and then just does it. And so this is a simpler approach. And if you think about things like Linux, for example, Linux wants to run on as much hardware as possible. So I should just support 2 rings, because not every processor has 4 rings precisely. Okay, and then you have this other thing, level 1. Guest operating systems, I don't know how many of you are using VirtualBox or VMware or whatever for running guest OSs on your system. It's a great idea. Like, I have both Windows and Linux running in guest VMs on this laptop. Not right at the moment, but typically those guest OSs, if you think about their life, the host OS is super happy because it gets to talk directly to the hardware. The guest OS is frustrated because it wants to talk to the hardware, but it can't because the host OS is in the way. And so a lot of times what happens is, especially when you have hardware virtualization support, the guest OS will run at ring 1, and then it'll get some access to hardware, so it'll have some optimized hardware support, but then it still has to interact with the ring 0 software, so it'll have to interact with the kernel to perform some operations. Okay, so the mechanism is really interesting. I don't have a lecture about it in the OS class, but I think it would be something that would be fun to talk about. Anyway, so level 1 is oftentimes where guest OSs end up living when you have hardware virtualization. Any questions about this? All right. Let's see. So yeah, you do need to be very careful when you're moving between these various privilege levels. You may have heard of privilege escalation exploits. These basically involve taking advantage of bugs in the operating system kernel to do something that you really shouldn't have privileges to do. And it can happen in a couple of different ways. One is you can sort of pretend you want to do one thing, and you get into the kernel and take advantage of a bug, and then you do something else. And these are sort of the most common kind of privilege escalation exploits that have occurred over like the last decade or so. Okay? So you basically use the same kind of exploits as we talked about before. I have this actually. You have a buffer overflow issue, or you can take advantage of some error in the code execution. There was some. You guys may have. There's actually a really recent Apple bug that allows you to do privilege escalation exploits. I can't remember what it's called. And there was one maybe 4 or 5 years ago where it was some really stupid error in the code, but nobody caught it. And so it allowed you to do things at a higher privilege level than you were really allowed to do. Okay, but there's other kinds of errors that you can have as well. Things like interacting with the disk is privileged because you're interacting with hardware. And so one of the things, there's a couple of operations that we'll talk about in the future, but you have read, write. And so what you do when you say, I want to read data from this file, is you say, here's the file I want to read from, here's the buffer that I want to use, and go ahead and read this many bytes. Well, the application typically would say, here's a buffer that I have access to. But what a naughty application could do is say, well, here's an address to a buffer that I want you to write into, but that address is actually something only the kernel can access. And if the kernel wasn't clever and say, I'm going to verify every address that comes in from the application, it could blindly do that and then overwrite data inside the kernel. And so the OS has to be extremely untrusting of applications. And so it verifies every pointer that comes in, every value that comes in. The OS has to do that kind of stuff. And if it doesn't, you can easily have the OS compromised by a naughty application. Okay? We talk about that a lot in the OS class because that's really important to make sure you do correctly. In fact, there's test code that actually tries to violate your kernel's protection constraints to make sure that your kernel is actually reliable, so that you can't crash it, you can't get it to modify its own state, things like that. Okay, so enough about that. Privilege escalation exploits are interesting, but certainly not the point of today's talk. So let's see, privilege levels. So another thing that's nice about IA32 is that each privilege level has its own stack. And this prevents a whole category of issues that you could have if the privilege levels actually shared stack space. Okay? You can imagine a situation where an application is being really irresponsible with its stack and it's using up most of its memory, and then a hardware interrupt occurs and the kernel has to somehow try to use what little stack space the application has left. Why even mess with that? Let's just give the kernel its own stack, and that way the kernel will always have space to handle requests. And it turns out that you don't actually need that much space because kernels don't have like deeply recursive function invocations and things like that. And so like 1 kilobyte or 2 kilobytes often is more than enough space for the kernel to do its work. And so the kernel can just set up a little stack for ring 0 and then give applications however much stack space it wants to. And then the kernel can be sure that it'll be isolated from the application. The one drawback of this is that it makes it a lot harder to pass arguments to the kernel through the trap handler. Okay? And so there is support in IA32 for passing arguments on the stack through call gates. Like you can actually say, hey, copy these arguments to the kernel stack. But exception gates, you just don't use the stack to pass arguments. You just pass them in registers. Okay? So it's a little bit more challenging. You have to give a little bit more careful thought when you're making this transition from ring 3 to ring 0. Okay, so we're going to talk about how int works, and it's complicated, and I apologize up front. Okay, so what happens? IA32 interrupts. I want to transition into ring 0 or whatever. I want to transition to another ring. Basically, it's very similar to the way a call works. I say int n, whatever n is, and the processor saves the address of the next instruction onto the stack so that I now know what to go back to. Okay? The other thing is that it saves the flags register, and this was because of the things that I was discussing before. Because we may interrupt a comparison operation. We may be in the middle of a comparison operation. So let's say that we had this code. I want to compare something to ESI and jump to the end of some loop. Well, if I have an interrupt that occurs in between those two things, I need to make sure I have the previous version of the flags register so that the code can pick up immediately after it returns back to this location. Okay, so that's the first reason. That's a very obvious reason. Now the second one is a little bit more subtle. You have application code executing, I have a hardware interrupt occur. If we go to the hardware interrupt handler that the operating system kernel provides, and it is written badly. And what happens is the interrupt occurs again while I'm in the hardware interrupt handler. What do I do there? Do I interrupt the hardware interrupt handler? That would be bad. Anybody ever had this happen on like W51 where you have interrupt handlers that are slow and they interrupt themselves? Yeah, that's exactly, the hardware does that automatically. But yeah, you can definitely run into that situation if you're not careful. You can actually have that occur in the operating system as well if you have a kernel that can preempt itself. You have one hardware interrupt occur, and you'd like another hardware interrupt to be able to interrupt that first hardware interrupt. So you can manually turn the blocking of interrupts off. I'll talk about that in a second. So, but this is also another reason why we save the flags register, because there is an interrupt flag that automatically disables hardware interrupts when a hardware interrupt occurs. Okay, so like I say here, when it's set to 1, when this interrupt flag is set to 1, interrupts are enabled. When it's set to 0, maskable interrupts are disabled. And so when you have a hardware interrupt occur, it automatically disables all other hardware interrupts. Okay? So that a hardware interrupt handler can never be interrupted. Now, like I said, really well-written kernels will actually allow hardware interrupts to interrupt other hardware interrupts. It makes for a very responsive kernel, which is why we like to support that. But if you want to make your life simple, you just don't allow hardware interrupts to interrupt other hardware interrupts. Like I said, take the OS class if you want to learn about this stuff, because we get into all this gory detail in a lot of low-level detail. Okay, so like I say here, the interrupt exception operation itself usually changes E-flags automatically. So this is only occurring at hardware time. If I have a trap handlers do not automatically disable hardware interrupts. Okay, so it's only when a hardware interrupt occurs, it changes E-flags automatically. So we want to save the old value of E-flags so that we don't lose that change. Let's see. So when we return from the exception handler, E-flags is restored, which automatically re-enables maskable interrupts. Okay, this is what I was saying before. Traps do not disable hardware interrupts, so that doesn't clear the interrupt flag. And there's also the non-maskable interrupt, which is for really critical stuff that the OS has to respond to regardless of what else is going on. Okay, it's called NMI. I don't know, has anybody heard of this acronym NMI before? Okay, so NMI is the non-maskable interrupt. So even when you clear the interrupt flag, a non-maskable interrupt can still occur. Okay, and you can see, like I say here, NMIs will self-block themselves. So a non-maskable interrupt can't interrupt another non-maskable interrupt. It just keeps things simpler when you have this stuff. Okay, so like I say here, operating modes have their own stacks. Exceptions may also need to change the stack. And this is one of those weird things, again, that the kernel has to deal with. And you have to think about all this stuff when you write an operating system kernel. I'm in the application. I invoke a trap. I change protection level. So I also have to change stacks. While I'm in the trap handler, a hardware interrupt occurs. Well, I'm in ring 0, and I change over to the trap or the hardware interrupt handler, which is also in ring 0. I don't have to switch stacks. So I have to think about these kinds of situations as well. So the interrupt sequence is like this. If I'm changing privilege levels, change the stack as well. And you can see that there's various bookkeeping details there. I save the caller's return address onto the handler stack, because the handler is what has to go back. I save E-flags, and then I can go ahead and disable interrupts as well when I go into the handler. Okay, so these are the details of what happens during the interrupt dispatch. Okay. Now, one thing that I want you to see. This is all done by the hardware. This is not a free process. Traps are expensive. They're actually less expensive than context switches, but still, trapping into the kernel is not like a blisteringly fast thing to do. Okay? And so that also affects how we like to design our operating systems and how we like to design our application. I just want to point that out as an aside. This is not as expensive as a context switch, but it is still not free. Now, we had all that stuff that happens when you invoke an interrupt, And so you have to do all that stuff in reverse to get back to wherever you came from. And so we have another instruction called IRET, return from an interrupt handler, that does all of that stuff in reverse. And remember, we're on a particular privilege level stack, and so as we're going back, we need to say, well, do I need to change back to the callers stack or the interrupted code stack? Do I need to restore e-flags and all of that kind of stuff? So it does these things. Restore e-flags from the stack, restore the instruction pointer from the stack, so we go back to wherever it was called from, and part of that instruction pointer encodes whether or not I'm changing privilege levels. That's how this works. So there's actually a little value that's part of the instruction pointer because it's a fully specified address. And if we're changing privilege levels, then it goes back to the caller stack using the information that's saved on the handler stack. So it's able to unpack all that stuff. Okay? This is all handled by the hardware. Okay, so that was all very complicated, and if your eyes blurred because of the details, I'm not surprised. Really, the only place you have to be aware of all this stuff is when you're writing OS trap and interrupt handlers, and there's some really cool macros you can use to do that kind of stuff, so it's really easy. Turn it into a simple table of stuff, and you can just dispatch into a handler to handle all that kind of stuff. But anyway, it's gory because we're interacting with the hardware, and the OS has that unfortunate reality. But we do have a way now of actually getting from applications into the control process, and also for the control process to interrupt applications that may be running. So we can actually context switch away from a process if it's been using the processor long enough. Or if it decides to misbehave, we can intercept that and actually do something about it. Okay? So context switches, we create an interrupt handler. The hardware timer is not accessible in ring 3. And you're not allowed to do it. So only in ring 0 are you allowed to configure that thing, because it's actually part of the programmable interrupt controller. You say, hey, set a timer, go off every 20 milliseconds so that I can switch programs. Okay? And so we set that handler to run in privileged mode so that the kernel gets invoked and it can access everything, including the application that's currently running, to save its context. And so like I say here, we suspend the application, copy the context out somewhere, switch to another process, copy its context in, and then we can return from that handler, and the other program that didn't have the processor now has it. It has no idea that all of this occurred. And this can all happen completely transparently to the applications. Okay? Any questions about this? So that's context switching, at least the mechanics of it. We haven't talked about all the detail. Also, a process misbehaves. So it tries to access a memory address that's not valid or something. Well, we know we'll get a fault from that. And so again, the control process, or our operating system kernel, can register a handler for that fault. And it's very interesting how they work, because the control process knows which application process is currently using the processor. It knows that because it said, you're using the processor now. And so when it gets that fault, it knows which program generated the fault. And so it can say, can I resolve this? No, okay, you die. It can go ahead and make that decision. And then once it's cleaned up after that program is exited, then it can switch to another program and let it resume running. So you can see now how one program behaving badly no longer affects the entire system. Okay, and again, I want to ask, are there any questions about this fault stuff? We're going to go into it in a lot more detail when we get to virtual memory, because there's a lot of different ways that we can handle a fault depending on the circumstances. But this is the basic idea. The control process knows which process it decided to start running, so when the fault comes in, it knows whose fault it is, and it can go ahead and just handle it appropriately. Okay? Let's see, so virtualization, we've basically defined how virtualization can work for our process abstraction. Like I say, it is very important in operating system implementation and also in the way that processors work. In fact, it wasn't until, I think it was the 386 that really introduced protection levels on Intel x86 processors. The 286 didn't have it, the 186 didn't have it, and the 8086 didn't have it. What that means is that you could not write a good operating system on those processors. You couldn't write an operating system that actually would do preemptive multitasking, that couldn't be compromised by a program, that would allow programs to remain isolated from each other. It was like the Wild West. You know, you get your revolver, you storm into somebody else's house, and you take their things. Okay? You can't do that starting with the 386. And so that, you know, with the hardware support for that, that's where we actually started having good operating systems running on the Intel processor. Now, other processors have supported this kind of stuff for a long time. Unix would run on different kinds of systems and so forth. So, but anyway, once we have that hardware support, we can start doing all these really neat things. We can have multiple programs running on a single processor at the same time. We can isolate the address spaces. We haven't talked about that yet. So we'll talk about that in the future. Yeah, so, and then we also need to think about, when do we do these context switches? And it turns out that there's really clean, good ways of doing that. Okay, so we have exceptional control flow that helps us with that. Operating modes and privilege levels. I already spent a lot of time talking about all of this. But you can start seeing that this is where the OS steps into the picture and why it's so critical, why it's so central. It's the thing that mediates access to the hardware on behalf of the applications. And so relying on these hardware facilities, we can actually provide all these things very effectively. And so we can have a useful and effective computer that we can use for various operations and even multiple things at once. So any questions? That's it for this. We'll go ahead and pick it up on next time, whenever that is.